So welcome back, everybody. And this is sadly the last week. Some people may be relieved and happy for that. I always have a kind of strange feeling when the semester is over. Anyway, what I wanted to do today, since we are trying to wrap up this discussion about the copper cluster approach, I wanted to try to finalize the stuff which we started with last Thursday. So last Friday, we decided to spend time on the second midterm. And that means that there were some things which were unfinished and which I just wanted to finish now in connection with the copper cluster approach. And this deals with the copper cluster and doubles. And then I'm going to sneak in how to use diagrams so that you can see how you can set up the same equations which you get by doing the gritty-nitty contractions. And then we are going to use that when we then move over to a copper cluster with singles and doubles, because now we just took away the one particle, one hole excitations. This is in particular something which favors this pairing model, which you have been admiring now for the last 2 weeks. And what I also wanted to bring up again is something which we discussed loosely for those of you who were here last Friday, and that is how you could implement the copper cluster approximation with doubles only to the pairing model. So for the final oral examination, which I wanted to say something about tomorrow, then this is a possibility to actually, if you want to, in your presentation, if you want to add results about copper cluster theory, then you could have a presentation where you present the different methods we have studied. You can bring in your results from the second midterm with FCI, many-body perturbation theory, and Hartree-Fock. You were already in a Hartree-Fock basis. And then in the presentation, you could add copper cluster theory. So the presentation is essentially you making a presentation of what we have done this semester. And then what many people then like to do is to take the midterms and use the results from the midterm to illustrate the theories. And then you can discuss the pros and cons, like in this specific case, you have seen, like from the second midterm, that when the interaction is strong, then many-body perturbation theory starts to struggle. And you will see much the same with copper cluster theory as well. So this could be one way of doing the final presentation, where you have to make a presentation of 25 to 30 minutes, and then we have some 10, 15 minutes for questions. And the remaining time is just to wish you Merry Christmas or whatever you like. Then the material here, which we have this week, is essentially taken from this text, these chapters here. There is also a link to, in addition to the slides, which you're seeing now, and which I will come back to, there is a set of slides here where I actually took the liberty of bringing up latex slides on copper cluster theories with singles and doubles, but where we do the diagrammatic approach. So what I'm going to do now is simply to remind you of the copper cluster theory with doubles excitation only, and look at some of the terms which we get, and then use that one to switch over to a diagrammatic representation. And if we get time, then we are going to jump into the singles and doubles excitations, and we will use that one to remind ourselves about diagram rules as well. So this is roughly what we have, and this code is also something which you had available last week as well. So you will see many of the same things which we had in the slides last week, but we didn't discuss this because Friday last week we gave priority to the second midterm. So let's just dive out here and go into the whiteboard. So what I want to do first is actually to remind you of the ansatz which we did with doubles only, and then look at the equations which you end up having to code. and remind you of some of the terms which you get, and also try to finish the list of terms which you get and what the equations are going to look like. So this is essentially taken from chapter 9 of the textbook from Shavit and Bartlett. So, but let me step you through these elements. So what we have is this projection approach. In a way, as we normally call it, projected approach. So we have an ansatz for the ground state, psi 0, which is now given by the exponential ansatz. And 2 weeks ago, we discussed this in terms of both Fowler's theorem for one particle, one hole excitations. But then we also looked at the general case that this exponential ansatz, where we define these operators T as a chain of operators T1 plus T2 up to the total number of particle hole excitations which we can make. Then we showed that this ansatz is equivalent to what we had from FCI if we then can take into account all the possible excitations. So in FCI, we had an ansatz which we wrote in terms of an expansion, 1 plus this operator C, acting on the same ansatz for the ground state. And this C was simply what we call the correlation operator, where we had this P of H, and then we had this coefficient CH of P, which we get from diagonalization, acting on a Slater determinant, which then contains a given number of particle hole excitations. And this, just to quickly remind you of these things, this phi HP is actually a string of creation and annihilation operators, A, B, and this goes up to, let's say, let me just change this a little bit so that we have it in a slightly better notation. So we would have a particle state 1, we have a particle state 2, and I just leave this with dots here because we have many such particle states, and depending on how many we have, that defines the number of particle hole excitations. And then we would have an I of, let's say, an N here, and then an I of N minus 1, and this goes all the way down to A of I 1 here, like that. And this would then be an N particle, a given N particle, N hole excitation. And this is then multiplied with the ansatz for the ground state. So that was roughly the setting which we had. Now we have also now assumed that this operator T can be approximated with T2. And this T2 is just the sum. So this is an operator. And that's why we have the factor 1 over 4, which means also that these unknown amplitudes, T, I, J, A, B, they have to be anti-symmetrized. And that's why we have the factor 1 divided by 4. And this is then multiplied with an AA, AB, AJ, AI. Now what we did next was then to write down the expressions which we get. So if we now take the Hamiltonian acting on this specific state, what we did was simply to act with the Hamiltonian of E of T2 acting on phi 0. And then we can just write out this operator by just taking the standard Taylor expansion. 1 over 2 factorial T2 squared plus, sorry. This should be a plus here. And this is multiplied with phi 0. Now, what we did next was actually to take the this equation which we have here, which in a sense, if you think of full configuration interaction theory, is something which is equivalent to psi 0, the exact function, multiplied with the exact energy with psi 0. And when we set up the equations in FCI, what we did then, when we built the FCI matrix, we multiplied from the left. So the first row was us multiplying with phi 0. Then we have the next row, which is phi I A. So one particle, one whole row, the two particle, two whole row, etc., etc. Does that ring a bell? And then we could set up the final FCI Hamiltonian matrix, which we then diagonalize. And when we diagonalize, we have the coefficients of the wave function. Now, here we're going to do exactly the same. And what we want then, what we obtained last week, was that when we did this multiplication, when we had phi 0, so this would correspond to the first row, and then we had 1 plus T2 plus 1/2 T2 squared, etc. Then what we found is that this one is equal to phi 0 of h of phi 0. This is a term which we have already seen, and that was nothing but the reference energy. And then we had the next term, which was phi 0 with h acting on T2, which then acts on phi 0. And that was the only term which survived, because when we had a T2 term here, then we didn't have the possibility to match the excitations which we're looking at. So when we had a T2 squared, we would actually end up with a two-particle, two-hole state as a final state. And that cannot match this phi 0. So this term here, when we then switched over the term with E0 ref here, so if we now look at the expansion which we have, this expansion here is supposed to be equal to E0 times ET2. So this is an approximation. And what we said is that we label this approximation with CCD of ET2 of phi 0. Then when we multiply, and this is just multiplied, sorry, I forgot to, so this is multiplied with phi 0. When we then multiply with phi 0, we have also assumed that since this is psi 0, the ansatz for psi 0, then we get psi 0 overlap with phi 0, and we have assumed intermediate normalization, so we can put that one to 1. And then we subtracted EC, this term here. We take E ref over, and then we can define the correlation energy. So what we found then is that we could then define the delta E CCD, which is simply E, so this is roughly what we did last time, minus the reference energy, and that was equal to phi 0, and then we have the Hamiltonian of T2 of phi 0, and this is again a term which we found was exactly equal to a sum of AB ij, and then we have these coefficients Tij AB, and this is multiplied with the integral over the two-body interaction here. So this is a very compact expression when we only have two particle, two hole excitations. If we had one particle, one hole, there would obviously be an additional term. So in that case, we would have had an IA, TIA, and then we would have had this integral over F and I here, in case we had T1. Now, we don't have T1 here. And if you think back to the pairing model, this is a reasonable ansatz for the correlated wave function, because if we don't break any pairs, then there is no way this T1 can enter the picture. So that's why I also provided you with a program, because if you want to compare different many-body methods, this pairing model is a very simple way of setting up a comparison. But where you have made an approximation in your many-body theory, where here you then have an operator T2 only, so we have this approximation which we have set up here. So the next thing which we did was then to take the same equation which you have here, this H times ET2 phi 0, and then we set up the equation where we multiplied with a phi IA. However, this one is automatically equal to 0, because in our case, we don't have any one particle, one hole excitations. So we don't need to consider that one. So this is exactly equal to 0, and we can just leave it out. The term which becomes interesting for us is the one which we looked at last time, which is ijab, and then we have h of et2 of phi 0, and we want that one to be driven to 0. But in our case, what we have now is obviously an ECCD, and then we have a term here, phi ij, AB, and then we have E of T2 times phi 0. Now, when we manipulated these expressions, we found several terms which we need to calculate. So this expression which you have to the right here simplifies, because we can have, this is just 1 plus T2, etc., etc. And the only term which then would survive would be a term with the T2 only. And then we would get the amplitude Tij times this energy ECD. So let's just look at the right-hand side quickly, and then we are going back to the left-hand side, and we're going to set up the different terms which we also put up last time. So if we now look at these expressions, what we would have is a phi ij AB, and then we have the Hamiltonian, and then we have 1 plus T2 plus 1/2 T2 squared, etc., acting on phi 0. And this is equal, and then this is just a constant, so we can just put it out here. And then we have this term phi ij AB, and then I have 1 plus T2 plus, and this is phi 0. And obviously the first term has to be 0, the one with the 1 here, because then we are just taking the overlap between two states which are orthogonal. You will also see then that if I have a T2 squared, then I'm going to produce 4 particle 4-hole excitations. And that will also be a term which disappears. And on the right-hand side, the only term which actually did survive was this term here, where we now have a phi ij AB, and then we have this operator, 1/4, and now we have to change labels. We have KL, and then we have a T, KL, CD, and then we have multiplied with AC dagger, AD, AL, AK, acting on phi 0. Now, this term, when you do the contractions, there is only one set of contractions which are possible. So this is just to remind you, this is a 2-particle 2-hole state. So this guy here is actually given by phi 0. And then I would have an AI, AJ dagger. So this is just a transpose, an AB and AA. So that's that state. And when I then do the contractions, you see then that the 2 holes here have to marry the 2 holes here. And then these two have to accompany this one. So that term simply reduces to an ECCD times the unknown amplitude Tij AB. So I'm just repeating some of the things which we went through last time. And then when we now look at the Hamiltonian here, obviously the Hamiltonian contains the reference energy, but it contains also the 1-body and the 2-body operators. So this is the left-hand side, no, sorry, the right-hand side. I'm still mixing left-hand and right side. Right. I don't know what happens. So in this case, what we have now is a reference energy, which is just a constant, plus the 1-body operator, plus the 2-body operator. And then we have this expansion of 1 plus T2 plus 1/2 T2 squared, etc., and multiplied with phi 0. And this is equal to ECD. And then we have a term here where we now have a Tij AB. Now, what we are going to get then is, if you look at the first term, so this one multiplied with this as a constant, that simply, and 1, that simply gives us 0, because then we are trying to match this state with that state. So the E0 ref is a term there which disappears. Then, if I multiply E0 ref with T2 here, then that is a term which can actually be non-zero, because I would have a T2 which I could then marry with this one. So this term with that term and this one is going to give me E0 ref times this Tij AB. So I'm going to get, that's the only term which survives there. So I get a Phi AB. Like, actually, I can just wipe it out here. So I would get E0 ref times Tij AB. And then if I shuffle that to the other side, then I have the correlation energy. And then I'm having new terms, and where I have to be a little bit careful, because I would have, and we did calculate, we did set them up last time. So I'm going to have an Fn, and then there's going to be an Fn with a T2. And we showed why last time, why we don't have a half T2 squared. So in a way, I'm just repeating some of the things. And then we got a new term where we have, so this can be different from 0. And I just wanted to remind you why. And then we have an AB, and then we have the next term, which is a V of n times, so the V of n, if we do that one with a phi 0, because that's multiplying, so I have a V of n times this one times that. So that's a non-zero term. And then I have plus phi ij AB, and then I'm going to get a V of n times this operator T2. And then there was a term which we thought could be non-zero, but where we have to be a little bit careful here. So there is a term here which we need to evaluate, which is 1/2 T2 squared of phi 0. All the higher order terms are actually 0, because if I have a T cubed, then I'm going to produce in principle a 6-particle, 6-hole excitation, which then I have to marry with an operator here, which is a 2-body operator, which can produce at most 2-particle, 2-hole. And then I have a 2-particle, 2-hole. So T2 cubed leaves us with a 2-particle, 2-hole state, which has to match the 0-particle, 0-hole. So this series actually truncates at a given order, which is defined, the given order in the operator, which is then defined by the type of 2-body interaction or 3-body or interaction which defines V of n. So these are the only terms which survive. And then that means that if we now look at the equation here, we have this ECCD. I can switch this over to the other side. And then I'm going to have this term, which is something we have calculated many times. That's just the overlap between a 2-particle, 2-hole state and the 0-particle, 0-hole state with a 2-body interaction. So this term here is going to give us, I'm just going to put it in here. That will give us a state, not a state, actually an integral, ij, so that's going to be that. So what I'm going to get then, when I shuffle this one to the other side, or I could actually put this one to the other side, it's up to you, decide which one you want. What I would get then is an AB, V of ij, and then I have plus this term phi ij of AB, and then we have the term with a Fn times T2 multiplied with phi 0 plus, and then we have a term here which is phi ij AB, and then I have V of n times T2 and phi 0 plus, and then I have the final one, ij AB, and then I have V of n multiplied by 1/2 of T2 squared of phi 0. And this is going to be equal to delta ECCD multiplied with the unknown amplitudes. And just to remind you of what this one looks like, this is actually given by a sum over CD KL. We have the unknown amplitudes KL, CD, multiplied with the element AB, B, sorry, not that, but CD, V, K of L. So what you see then is that you have a set of equations which are nonlinear in the unknown coefficients T, I, J, A, B. Because we have T, I, J, A, B here, but we also have it here. So we typically call this a nonlinear equation. And you will also see that this equation, which you see here, brings in a nonlinearity because it will have the coefficient squared, since you have a T2 squared here. Okay. So if I put this to the other side, I'm going to have 0. And then you get an equation, a nonlinear equation in the unknown coefficients. So if I just shuffle this over, then you have equal to 0. And then you would have a nonlinear equation, which are typically solving by finding the roots of the problem, because you're driving it to 0 on the right-hand side. And that means that typically what you will do then is to start with an ansatz for the amplitudes and then iterate till the energy converges, till it doesn't change by more than a factor which you have set. So this is essentially a application of the Newton-Raphson method, where you're finding the root of an equation. And this is actually a standard recipe which is being used in copper cluster calculations. So simply switch this over, and then you have equal to 0, and then you find the roots of this equation for the unknown coefficients, starting with a guess. Okay? That's the basic algorithm which we are coming back to when we look at the program. So let's now go back to these lovely expressions which you have here. I can see the excitement of being reminded of how to calculate these guys here. So let's take a look here at the different terms and see why they are non-zero. I'm going to set up the equations, but afterwards, the reason why I wanted to bring this up is that I'm going to bring in the diagrammatic representation of these operators. And then by looking at the diagrams, you can actually connect bits and pieces of the diagrams and then figure out the equations without doing all the boring algebra, which I'm going to do now. Doesn't that sound nice? Okay, so let's look at these expressions and let's remind ourselves about the first term. So we have ij, ab, and then we have this fn, and then we have t2, and then we have phi 0. Now, fn is just the sum over all the possible PQs here. And we have AP dagger, so this is a one-body operator. And then we have an integral over P, and then we have this F and Q here. We just leave it unspecified. This is just an integral over one body type, over one particle type. That means that when we now look at this, so if we break this down, what we are going to have now is a set of contractions which need to be done. So if we take now and just look at the contractions, we are going to have an AI dagger. We're going to have an AJ dagger. We have an AB, AA. So that's the state which we have on the bra side. Then we have the operator AP dagger and AQ. And this is now multiplied with the operator, which now has an AC dagger, AD, and then we have an AL, an AK. And obviously we have the matrix elements or the integrals as well, but now we just look at these. So when we looked at this last time, so we actually did the calculations, but I just wanted to remind you of what we get. We could do then several things. So one is to keep the whole states fixed. So that means that we just contract them by themselves. So that means that the whole states are unaffected by the operator V of n. Then we need to match the operator. And you see now that for the operator here, we could have this contraction. And then we could have this one. then the other particle state, this B and D, they're just left unaffected by the one-body operator. So that means that what we would have then would be something like this. You see again that we can do this in different ways. And we could now, instead of having these being contracted, we could actually have this dude being contracted with that one. Then we could have this one with that one. And then this one would have to go to that one. We still keep the whole lines fixed. So if we do the contractions here, we are going to get 4 terms. No, sorry, we're going to get 2 terms for the one part, the one body operator. And let me just find back my notes here. Oh, I need to find, let's see, where did I leave my notes here? Just yeah, when I look at when I fix the whole states, what I'm going to get then is a set of equations where I'm going to have a factor of 1/4. And there will be a term where I sum over C, and then I have my A of F of C here. And then I have an amplitude, because you see now that this amplitude is left unchanged because I have a Tij, but then I have a C with A. And this is, no, sorry, TC. C with B, like that. And there is another term here, which is going to be equal plus a sum. So these are actually 2 equal terms, which we are going to rewrite in a more compact way a little bit later. But we are now having B instead of A, and then we have F, and then we have this D, and then we have the amplitudes Tij and AD. So this depends on the type of contractions which we are going to do here. And then finally, what we will have, actually there shouldn't be a factor of 4 here. I think the factor of 4 is wrong. So this should not be here. But then I have another set of equations which I can get. And that other set of equations is the one where I now keep the particles unaffected by the operator. And then I simply have the whole states being contracted for one particle at a time with the one body operator. So the whole states are going to give me a term which goes like minus. And now I have a sum over L, the whole states. Then I'm going to have an L, and then I have F, and then I have a J here. And then I have a T, I, L, and then A, B. So A, B is fixed now because I haven't changed the particle states because they are not affected by the one body operator. And then I have an additional term. So we just write it like this. So this is the whole term contribution. And then I have a sum over K, and then I have a K of F of I, and then I have a TKJ of AB. So this is for the one body operator. And we did these derivations last time. So everything which you see here comes from us either keeping the whole part unaffected by the operator, and then the operator acts only on particle states, or the operator acts on the whole states, and then depending on which one it acts, we get 2 terms here. Later, we're going to merge these terms because these are just summation indices. So C and D can actually be these terms can actually be rewritten in terms of the summation indices. So that's the one body term. And then we have the 2 body term. And if we look at the 2 body term, what we are going to get then is something like this. So let's just write down here the integrals which we are going to get. And let me find them here. Yeah. So let's, so we have a phi ij, and then we have an AB. And then we have the 2 body operator, and then we have the T2, and then we have the phi 0 term here. So let's only look at the operators, the creation and annihilation operators. So we just leave out the integrals and other constants. So this is going to give us a factor of 1 over 16. And then we are going to get terms of the following type here. So we will have an AI. This is the state which we have on the bra side. Then we have AB, AA. And then we have the two-body operator, AP dagger, AQ. So there's obviously a summation there. And then we have AS, AR. And then finally, we have the operator T2, which then gives us, so that gives one factor of 1 over 4. And then we have the other 1 over 4 coming from the interaction. So there's 1 over 16, there's 1 over 4 from that one, and 1 over 4 from that one. And then we have an A of C dagger, AD, and then we have an AL and AK here. Now, when you look at the contractions here, you can again say that, okay, I could now say that there is one type of contraction here which acts only with the particle states. So we could just leave the whole states unaffected. So we could just leave these two just unaffected. And you know that we can obviously here, we can interchange these two. So this AI can go to AK and AJ to AL. But AI could also go to L and J could go to K. So these are possible contractions. So when I mark it like this, it simply means that I now leave the particles, the whole states unaffected by the two-body interaction. Then we have a whole chain of contractions which we can do then, which involve the particle states. So if we just do this, what we would have then, this is a set of contractions we could have. And in this particular case, we have two possibilities because we can interchange. Here, we could have A going to C and R going to D. So that's the other one, which is non-zero. And then we have the contraction here between A and P and B and Q. So that's one possibility. Now, the other possibility is that we now take the whole states and let them interact. So let's just put up that one. So that's the next possibility. So we have, if we now just rewrite it, so we have AJ, AB, AA, AP, AQ, AS, AR. So what we are doing now is simply to let the two particle states be unaffected by the interaction. So they are just contracted with themselves. That means that what we need to do now is to have the whole state here. So these whole states have to act together here. And that means also that this has to match these two in one way or the other one. So when we do these contractions, we are going to get factors of 1 over 4, not 4 times. We have seen that before. So I hope you can forgive me if I don't go through all the types of contractions here, because this is just a matter of linking up the right Kronecker deltas when we have the contractions. So this is going to give us a given number of terms where we will get the following expression. So let me just bring them up here. Where did I put it? I just need to remind myself where I actually put these terms here. That was L1. I had written them down somewhere, but now I don't remember where I put them down. Yeah, we are going to get a series of terms here. So I'm going to label these terms in the following way. So there's going to be a term which so the terms we had previously, these ones, I'm going to call this for L1. And these terms are the terms which I get. I think there should be a factor of a half here, but I need to check that. The L1 are the terms which link the two-body operator. Then I have an L2A. And L2A is the case where I leave the whole states unaffected. So the L2A is going to give me a term here, which runs like 1/2. And then I have a summation over the states C and D. And that comes from the contractions which you see here. So the whole states are just fixed. So L and K have to be equal to I and J. And then I'm contracting with the operator, the particle states. And that is going to give me a interaction element, which is going to be equal to AB, V, and CD. And this is multiplied with the amplitude. So I and J are fixed because we have contracted the whole states with themselves without the involving interaction. And then there is a CD here. So that's the term L2A. Then we have a term which I'm going to call L2B, where we now look at the contractions between whole states and interaction. And that is going to give us a similar term, which is going to be equal to 1/2. But now we are summing over whole states, KL. And then the matrix element, or the integrals, are going to be given by IJ. Now, A and B are fixed now, because we had to contract the particle states with themselves. And this amplitude is also now involving the two whole states. So if you now look at what we have here, if you go back to the equation which we put up, so the equation we want to solve, which is this one, you see now that this term here is something we have set up, and that contains the unknown amplitudes. It contains these expressions, which we can calculate. Then there is an L2A and L2B term, which also contains the amplitude, the unknown quantities. Then there is a thing which we didn't say here, and that is that these guys here, we don't need to keep the two whole states or the two particle states not interacting. We could have one whole and one particle being contracted with this guy here. So we will actually get an additional term, which I'm going to call L2C. And this L2C here is actually going to be a little bit more complicated. L2C is then going to be given by a sum. So you might say now, what kind of simplification is actually copper cluster implying when we get all these ugly equations? So this is after we've done all the contractions, TI, K, and then AC, and there is a minus. So let's just write them up here. There is an LK, V, and CI here. I hope I put everything correctly. And you will see now that in these equations, the terms here, one of the whole state has been contracted with interaction, and one of the particle states has also been contracted with interaction. And then there is an A, K. So you see you have particle whole states. This state is a one particle, one hole. This is a one particle, one hole. Same with this one, that one. And also the next ones involve one particle, one hole states of CJ. And this has a TIK, if I done all correctly here. And minus, no, it's actually plus. And it contains a AK of V of C of I. So these are terms which you need to put into the equations when you're going to solve them. I will later show you how you can calculate these efficiently. And this is something which is called intermediates, because you can perform some intermediate multiplication and store these quantities. And actually, just to give you something more, a hint of that, if you look at this term and this term, you see you have a C and D here. You end with an I and J. You can set up a matrix with A, B, and C, D. So this could be rewritten as a matrix. This is rewritten as a matrix. So the way you would calculate this is to set up matrices of these integrals and then calculate efficiently and perform matrix multiplications. And some of these terms here can actually be calculated as intermediate terms because they will appear in other terms. We will see that a little bit later. So this is the final term which you get from, if we now look at this term here, that one. So after the break, we are going to enjoy the final term, which is going to be phi ij, ab, and then we have a v of n, and then we have 1/2 and t2 squared of phi 0. I'm not going to run through these calculations in full detail because I'm going to show you how you can set it up, but then we will be using diagrams to actually set up the final equations. And that is a much more compact way of actually setting up the final equations. And that gives us a very, how to say, convenient algorithm or convenient approach to find the relevant expressions. But now we are doing the algebraic efforts and we are setting up all the terms by looking at the contractions. These are things which, if you use software for weak contractions, you can actually automatize this. And if you look at the terms which I put up here, it is not exciting to actually go through all these contractions. I did it once, and this is not something you want to do again and again because you don't gain any new insights. And it's so easy to lose some coefficients. So these contractions, you have actually packages where you can do the weak contractions, and they will find the final terms for you. So, but it's okay to have seen the basic procedure. Okay, you take a small break. So what we are going to do now is just to look at the two of the possible contributions, because intuitively, when you look at these terms, you would think that T2 produces a 4-particle 4-hole state. But then we know that the Vn can take away a 2-particle 2-hole state. And then we have a 2-particle 2-hole state here. So that means that if we now count the number of possible excitations we have, T2 could create two 2-particle 2-hole excitations. We have a 2-particle 2-hole excitation here. And then we have the possibility of a 2-particle 2-hole excitation in V of n. So it is possible that this term here can actually give some contributions. If I have T2 cubed, then I'm actually producing 6-particle 6-hole excitations. And I want to end at a 2-particle 2-hole excitation. And then we know that if we have a 6-particle 6-hole excitation and an operator V of n, which can at most take away one of them, then the T3, the T2 cubed, T2 to the power of 4 and so on, will all be non-zero. No, sorry, will all be 0. Sorry. So let's take a closer look at these terms here and look at one possibility. So when we look at this term V of n of 1/2, so what we are going to have then, and I'm going to call this term Q1. So I'm following closely what is called chapter 9.3 in Shavit and Bartlett, where they do the algebraic derivation of all the expressions. So this term has then something which runs like this. It's a phi 0. Now we do have a summation over all the different states, but I'm leaving out this. I'm also leaving out the specific integrals for the two-body force and also the amplitudes. But what we're going to have then is something like the AI, AJ, AB, AA. So this is our bra side. Then I have the two-body operator. So I have an AP dagger, an AQ, and then I have an AS, AR. And then comes a T2, and then a new T2. So what I will have then would be something like an AC dagger, AD dagger, and then I have, so let me try to, let me just wipe this out and squeeze it into one line here. Because This is just going to go over 2 lines here. So let me just redo it. And now I skip the state we end with and start with. So AI, AJ, and then I have AB, AA. So this is my bra side. I have the 2-body operator, AQ, and then I have an AS and AR. And then I have the next one, which is an AC, AD, creation operators, and then I have an AL, AK. This gets exciting, eh? And now I'm going to have the next one, which will be a new operator here. So there's going to be an AE. So these are particle states. And then I have an AN and an AM here. So I'm having 4 sets of 2-body operators. And what I could say now is that the 2 whole lines, as we did before, so we could now simply say that one possibility is that we keep the 2 whole states fixed. So these 2 have to match each other. And that will then fix some of the indices. Then what I have to do is to perform the other contractions. And you can see now that the other possibilities which we have would be something. So what I could do now is to say that these states here are now also states which are not affected by the interaction. So if I take these 2 guys, I could now say that one possibility is that these 2 guys here, they are now coupled with these 2 guys. So now you start to see why this can be non-zero. So we have in the final state, we actually coupled the single particle states with the single particle states of the T2 operator, which acts to the right of the equation. So that means that the contractions which then become important for us to look at here are actually the ones which involve these terms here. So this would be a typical 2-particle state which is being created, and then we have the whole states here. So that's a possible contraction which we have. And this will give, when we do all the contractions, so we are going to have a factor of 1/4 here. So this will give us, this gives us an amplitude originally, which is MN and EF. This other term here has an amplitude, which is TL, TKL, and CD. And then the interaction here has a term which goes like P, Q, and then we have V, R, and S. And when we then perform the contraction, so we're going to have a factor of 1/4 to the power of 3. But then when we add all the contractions, we are going to get a factor of 16. So we will be left with just 1/4. So this term, when we collect everything, this term Q1 is simply going to be equal to 1/4. And then I will have a sum over K and L and C and D. So the interaction matrix elements are locked because they are contracted with one of these states. And then I'm going to get a term which goes like KL V of CD. And then I have the unknown amplitudes, but now they are squared. And you see that they have CD here. So I and J is fixed. And then I have T, KL, and A and B. So if you look at this equation here, this is actually now going to involve a 2-particle 2-hole state, a new 2-particle 2-hole state, and then it's multiplied with an integral. So we are going to, instead of going through the gritty-nitty derivations of all the terms, there are actually 3 more, and they come from the different ways you can organize these terms here. But we are going now to look at this from a diagrammatical point of view, because it's easier to visualize what is taking place. So, but you see the basic procedure. So if you want to calculate these terms, you have then to look at all the possible contractions. I mean, this gets pretty boring, and it's very error prone if you do it by hand. And this is something you would simply put into a program which finds all the all the contractions, and then you can clean it up and get the analytical expression, which is the one you have to program at the end. Now, I just wanted to give you one intermezzo here before we start looking at the diagrammatic expansion. Now, if you look at this term which you have here, this one, so just take a close, if you look at that one, so you have a 2-particle 2-hole amplitude, and you have a 2-particle 2-hole integral. This is something now, if you want to set it up in a very brute force way, and you run over all the 4 indices, this is going to require a lot of CPU cycles. So the standard way you would typically do this is to pre-calculate this term here. And you would pre-calculate it as the multiplication of 2 matrices. So you could now think of this as a matrix V, where K and L is an index uppercase letter I, which just refers to whole configurations. And then C and D would be a matrix now, which has another subscript A. So you have particle, the whole states, and particle states as configurations. And then you simply set up a matrix which now contains the possibilities. So it means that you would then encode these integrals as a matrix, where I now contains the information. It's a pointer to all the possible 2-particle states you can make. So if you can make 100 2-particle states, then obviously this has a dimension of 100. And if you have 10 2-hole states, this matrix has a dimension 10 times 100. And you see now that this is also something you could rewrite as a matrix, where you now have a CD, which we just call, so we call that for configuration A. So you could think of this as a matrix A, and then it has obviously I and J. So you end with I here. So it means that the summation over C and D is something you can rewrite as a matrix multiplication. So these two together, they could now define an intermediate, which then will depend on the states which you have available here. So that would be K and L. And it would also be A and B at the end, because you want to multiply this with this guy here. So this is a quantity now, this one is a quantity you could pre-calculate. And if you go back to what we had earlier, if you look at, for instance, a term like this one, it is also something you could pre-calculate. So these are all kind of lookalikes, which can be pre-calculated. And when you have these terms which include the amplitude squared, you would then simply pre-calculate this matrix here, and then you would multiply it with this as a matrix. This is the way you implement this numerically, and that saves a lot of CPU cycles, because you would simply set up the relevant matrices, and these are matrix multiplications can actually be parallelized and be calculated efficiently. Okay, that was just a technicality, just an aside. Now, I'm not going to, harass you with all the derivations of the possible terms here. You can find this in a textbook by Shavit and Bartlett. And what we are going to do now is to look at the diagrammatic representation, because we're going to use that when we are setting up the T1 and T2 or copper cluster singles and doubles. And you will see this becomes even more powerful when you look at 3-particle 3-hole excitations and so on. So let's bring in a diagrammatic derivation or diagrammatic representation, or whatever we call it. Perhaps we call it approach a little bit better. So let's now take a look at the amplitudes and how we can represent them diagrammatically. So this amplitude T2, which we have, This is something which we diagrammatically, we know that it's given by 1 over 4. And then we have a sum over A, B, I, J. And then we have this T, I, J. This is the unknown amplitude. And then we have the operators here. We can represent this diagrammatically, since this Tij can then represent processes which we have summed to higher order. So if you now think of the equations which we are solving, so let's just pull back a little bit. When you look at these equations, every time we update the parameters here, it means that we are adding higher and higher order contributions. So a typical guess here is to start with this one as, so the Tij AB, and if we put 0, this the standard guess here would be to use perturbation theory, where the operator is to first order, like you did in the second midterm. Then you would plug this as an ansatz in the equation, your guess, and then you would keep iterating this equation. So every iteration, you're building up on this Tij higher and higher order terms. So that means that when you represent this operator as a diagram, what we are having then is something which we would write like this. So we have the whole states. So this is a diagrammatic, and the bar here is in a way to indicate that it's actually something which could be beyond the interaction to first order. And it also indicates that this Tij contains energy denominators. And it's also a term which is dimensionless. And you saw that from the first order term, that you have the integral, and then you have divided by energy. So it's a dimensionless quantity because the numerator has dimension energy and the denominator energy. And then we will simply put labels I and J, A and B. Now, I'm going to also give you a labeling here, and I'm going to call this for excitation level 2. What does that mean? It means simply that I have a 2-particle, 2-hole state. So I have 2 1-particle, 1-hole excitations. Okay? So I create 2 1-particle, 1-hole excitations. So it's a 2-particle, 2-hole excitation, and label this as excitation level 2. So I am actually bringing my system from the ground state, for instance, to an excited state. So this is actually what this operator is doing. So it creates an excited state. So that's a T2. But let's now take a look at the Hamiltonian which we have. So if we look at f of n, we know that this one is actually a sum of a PQ, and then I have AP dagger, AQ, and then I have this integral, P, this operator F, which we have just left unspecified. We know that this one is actually a sum over A and B. So we would have A, B. So these are the particle states, F and B, plus, and then I have my AI here, and then I have AI, and then I have my A, F of I, and plus. Okay, so there are 2 more terms. So I can depict these graphically as following. So the first term here is something which I can write like this. So I have my interaction here, I just leave it like this. Then I have a state A coming out and a state B. The second one, there are actually 2 terms to the second one, which you see here. There's going to be one where I create a particle whole state, which looks like this, AI. But then I do also have the possibility, so I just put dots here because, or just plain laziness, because you see quickly that there is a case where you have an A coming in and an I leaving here. plus finally this term here, where I then would have an I and a J here. Okay. I can also give excitation levels to these. So this one has level because you create a one particle whole state. So I would say this is level +1. This would then be level -1. Here I have no particle whole state. So I just call this level 0. And the same with that one. Okay. So when I don't have any particle whole states, then I just put 0. So it's just a way to label the processes here. So this is the one body operator, but then we also have the two body operator. And now what I'm going, so it means that we would have to break this sum, this 1/4, and then we have the PQ, BRS. We would have to break that one into many, many different sums. But what I'm going to do now is simply to set up the possible diagrams. So instead of breaking them up in sums A, B, C, D, A, B, I, J, etc., I'm simply going to set up the possible diagrams which you can have. So this is diagrammatically, it's going to be something like this. So there will be a particle one. So we call that just for A, B, and C, D. I'm putting arrows here. And at the end here, I'm going to skip the labels. I'm just going to put arrows. Is that okay? So this is obviously level 0. I don't produce any particle whole pairs. I have a next one here. So this, when I write it out, it's going to look like this. So I have this diagram, and then I have this one. So this is a one hole coming in and out. And in this specific case, I'm having a particle whole state above and one above and below. So this is also a level 0. So there is no surplus of particle hole excitations above and below the vertex. Then I can have more diagrams. So one which I can have now is, so let me just, this is just the exchange of that diagram, which you saw now. I could have this one. And this is also a level 0 because I have one particle whole state below and one above. But then when I then go to this case, and where I have particle states, this is something which I will call a two particle one hole state, because I have a one, actually it's a three particle one hole state, because I have three particles and one hole. And in this case, this is a level 1, because now I have created a particle whole state here. And then you see that I can continue. So I could have a state like this one. So this is the kind of terms you get when you write this PQRS sum in terms of particles and holes. So this would be a level which I will call -1, because I am actually destroying a particle whole state. Then we have new terms. We have this one, which is a two particle two hole state. And we will call this on level +2. But that means also that there has to be a companion here, which is the level -2. So this is us destroying a two particle two hole state. And then we can continue with this one, where I then create a particle whole state. So this is a level +1. And then I will have a whole state here. And this is a level -1. And finally, I would have the two hole state here, coming in and leaving. So this is a level equal to 0. So these are the type of contributions which I can get when I write this generic two-body operator in terms of the explicit particle-hole correlations. Now, keep in mind that here I have only included the direct terms. I haven't included the exchange terms. So you would also have to include exchange terms, but we are just leaving them out, okay? That's pretty common in the literature, that when you draw these diagrams, you're assuming that this also contains the exchange term, but you draw only one of them. That's a kind of common but confusing way of labeling the diagrams. So where do we want to go now? So let's go back to one of these equations, which we had previously. And let's take a closer look at how we can set up a diagrammatic way to derive the same equations which we did before. So what we're going to do now is to look at these different terms which we had. So we had a phi ij, ab, and then we had the operator f of n, and this was multiplied with t2 of phi 0. If we look at the phi ij and ab, this is definitely a state which is a two-particle, two-hole state. That's where we want to end. So we want to end in a two-particle, two-hole state. That is going to be my final state here. So when I've done all these kind of manipulations, this is where I am. So we want to end in a two-particle, two-hole state, which then means that we need to have a level +2 excitation. This is where we need to end. So if we now look at phi 0, this is a level 0 because it's a zero-particle, zero-hole. So what I have then, when I bring pieces together, is that I now have a T2 amplitude. So this is my T2 in the equation. And then I need to match this one with one of the Fn operators. So this has to be multiplied with one of these guys. I can have this one, or I can have this one, or I can have this guy, or this guy. So this is a +1, this is a +1, this is a 0, and this is a +2 level. So I actually want to end with a +2 level. So if you now look at these diagrams which you have here, I start with 0. If I now take a +2 here and connect that with a +1, like that one, then I would end up with a free-particle, free-hole state, which is not possible. It would also be an unlinked diagram. If I take, one of these should be a minus. This is my bad drawing. So this is a -1, sorry. If I take this one and contract that one with one of these, what that would lead to would be a diagram of this type. If I perform the contractions, so I would then get something which looks like this. And that takes me from level 2 with -1 to level +1. Okay? So this is just a one-particle, one-hole excitation. But I want to end in a two-particle, two-hole excitation. So it means that the only guys which can contribute here are either this one or that one. So when I then link these together with these guys here, you see now that this guy must be linked either with that one or that one. That will correspond, if we now spool back a little bit, to this term which we called L1. That would actually correspond to either this one or that one when we did the contractions. So if I now look at the terms which I could get when I contract here with this one, with one of these four guys here, it's either this one or that one. So if I do my contractions with this one first, what I would get then would be something like this. So I could have this one, and I have the whole line which is not affected, and then I have this diagram here. But I could also get the other one, which is the other term I had, because I didn't simplify the equations here. I can actually, these are what we would call topologically equivalent diagrams, because these vertices here are symmetric. So the only thing I would need to do then is just to set up an expression where I have interchange the two particle Hall states. So I need to have an operator where I actually permute. If I now put labels to this, if I call this for I and J, and this A and B, and then this is again A and B, and I and J, these are going to be the two particle terms which we had in that contraction when we did it by hand, or not by hand, but algebraically. So I would actually rewrite this one just as one diagram, but then I have to take into account the fact that I can interchange the two outgoing particle states. So this would just be written out in terms of one diagram, and then we have to set up a diagram rule so that we get both terms. And then if we now put labels to it, we have an I and J, and then we have A, and we have B, and we have an intermediate C. So if I want to set this up, this is going to be given by an equation where I'm now summing over C. I have this vertex here, which is my B, and then I have this F, which I haven't specified, and I have C, and then I would have an amplitude which goes like Tij, and then I would have my AC, like that. That's the amplitude, because the amplitude is this one. So if you go back to what we had earlier, when we did all the nice derivations here, or rather we just showed some of them, this would actually correspond to the term which we have here, except that I have a slightly different labeling here. Nice music in the background. Somebody who plays hard rock here, he could compensate that sound with a hard rock, right? Couldn't we? Black Sabbath or something like that coming out. That's the kind of ideal way of doing Christmas, right? You start Deep Purple or something like that. Similar. Sorry for the digression. Okay. I don't know why, every time I hear that kind of music, I think of some hard rock. Anyway, what you see now is that we would have that diagram, and in order to take into account the permutations here, we would need to multiply this with a permutation operator. Then there is another one which we can link, and that is the whole part. And we could actually link that one with either this one or that one. So there will be a whole term, which then would simply be given by something like this. And actually, this is given by that. And then I have an A and a B, and then my I, and this is the state J, and then I would have a state K here. And this is actually when we now take into account the possibility that we can fix or attach this vertex here to this one. We're going to get 2 terms. So in total, we have 4 terms, but we would draw them. When we make the drawing here, we would just label one of them. But then we have to, when we want the final expression, we actually have to write down the possibility of an exchange here. Okay, so the next term which we could look at, so we have done this one now. So you see how, I hope you can see that this is something which we can build up in a very intuitive fashion. If we think of excitation levels and we just bring in the types of excitations together. If you look at the expression which we had for the energy, this d delta E CCD, that was given by 1/4, and then we had this term of AB IJ, and then we had the amplitude Tij AB, and then we had a matrix which was AB V, or an integral. I keep calling them matrices because I always transfer these objects into matrices. So if you look into this one, what you would have then is a T amplitude, which is this one. So this is our Tij AB. And then we have actually this is wrong, what I did here, because A and B should be interchanged. So it should be I and J and A and B. So if you look at this one is a level +2. But since we are going from the ground state to the ground state, we have to end up in an excitation level of 0. And the only way we then can match a +2 here is if we now look at a diagram for the 2-body operator, which is a -2 level, which is that. So the only term which matches this excitation here for the energy is then a term like this. So this is the T2, and this is the Vn operator. And that becomes equal to this diagram here. And if we were to do second-order perturbation theory, the bottom vertex would just be a standard interaction vertex. So we would have an A and B and I and J. And this is the way we would represent this term here. So the only possibility we can match this +2 excitation with, because we have the operator T2, and it's actually this term which you have is equal to phi 0 V of n times T2 phi 0. So phi 0 is excitation level 0. T2 gives us +2. And then we want to go back to excitation level 0. And then we have to match it with an interaction, which is now -2 here of excitation level. So let's go to the other terms which we have. And these are the terms which we label as a phi ij AB. So this becomes a state which is not the ground state. So that is a state which has excitation level +2. So we have to end in a 2-particle 2-hole state. So this has a level +2. And then we have the interaction V of n, T2, and then we have a phi 0. So this starts with the +0. This gives us +2. And that means that when we look at the V of n here, the V of n has now to be so that we end up with something which has excitation level +2. So let's take a look at what we have then. So we start with this one, which now has acted on the ground state. So this is the specific state which we have here. And now we want to end in an excitation level of +2. So that means that when we match V of n, we have to have excitation level equal to 0. So that means that if we now look at the diagrams for the operator, which could match this, it means that we would have to look at this one. So we could have a 2-particle diagram. We could have a 1-particle 1-hole excitation here. on this side and that side, or drawn like this one. So this is just the exchange diagram of that one. This has excitation level 0. Or I could have this one, which is also an excitation level 0. The other ones cannot match it, because if I attach an excitation level of 1, I go from 2 to 3, and that doesn't bring me back to a 2-particle 2-hole state. It gives me a 3-particle 3-hole state, etc., etc. If I have an excitation level of -1, then I would take away one of the particle hole excitations, and it brings me a 1-particle 1-hole state as a final. So the only one which can contribute then, if we look at this specific term here, is something like this. So we could now have, so let's just look at them. So we can bring in this one. We can bring in this one. And now I'm going to put up explicitly the 1-particle 1-hole term, which will be this one. So you can see now that this one needs to be contracted with the 2 hole lines. This one needs to be contracted with the 2 particles, which we have here. And this one would have to be contracted with that one. So we have a level 0 here, but we contract this one with that one. And then we are left with something which looks like this. So let's take a closer look at it. And we would get a diagram, one for the 2-particle case, which is going to look like this. And that is a term where I would have a sum over C and D. I have my I and J, and my A and B. So this is something which leads to a 2-particle 2-hole final state, but I have some intermediate excitations. So if we look back at the contractions which we did, so let's just go back in time again to before the break. If you now look at the term which we calculated and labeled as an L2A, you will now see that this one has actually an AB here, leaving. We have the TIJ, which is the whole state, and then we have this intermediate summation. So that diagram which we saw now is going to correspond to this term. So then there is also going to be another type of excitation here, which we have. So we said that we had the 2-particle 2-hole case there, where we have a 2-particle diagram, but we could also have the following. And then we have the 2-hole state here, where we now have an intermediate 2-hole state. So we have an I and J leaving, an A and B, and then we have the intermediate one, which is a K and L. Now, if we now look at the diagram rules, we have a pair of hole states which begins in the same vertex and ends at the same vertex. So as a factor over half, we have 4 hole lines. We have a sum over the intermediate states, K and L, and then we would have a vertex, which here would be an K and L, V, I, and J, and this will be multiplied with a T, A, B, and then I would have a K, L here. So this is the term for that diagram where the intermediate states are K and L. So if I go back to the analytical expression, which I found when I did all the lovely contractions, if we just go back to that one, you will see that I put up a term which looks like this: K and L, some K and L, I and J, T, K, L, A, B. Oh, by the way, I think I did a small error here when I wrote it out. Let me just correct. Okay, I just call it I and J here. Yeah, right. So that's the term which we get here. And similarly, this one, which you have up here, would be a half. And then I have my sum over C and D. And I have my outgoing states, A, B, V, and C, D. And this is multiplied with the amplitude, I and J. And then I have C, D here. And then the final one is the one which is going to be this term which we call L2C. So this was a term which we called L2A earlier. This is L2B. And then we have the final term, which is going to look like this, plus all possible permutations, which we're coming back to tomorrow. But our time is running out now. So I would have this one, and I get this. And this is also two-particle, two-hole state. So I would still have my A and B's, my I and J's, and then I have a particle-hole intermediate state here. And this would be a state C, and this would be a state K. And then we have possible permutations of these guys here. And I will show you the final expressions which we get tomorrow. So this is an extremely powerful way of setting up all the possible contractions. And finally, you can leave that as a small exercise, but I will set it up tomorrow. So if we look at this one where we had V of n and 1/2 times T2 squared of phi 0, then we see that we have level 0 here. This gives us +2, +2, and then we end with a +2 here, which means that when we are setting it up, we actually have two T2 amplitudes, like this, at the bottom. So this is what we create. We create a 4-particle, 4-hole excitation. These are these two guys here. And then in order to get into a 2-particle, 2-hole final state, one possibility here is actually to match it with an interaction of this type here, which has a level -2. So this will be linked with that one, this with that one, and that one, and this with that one. So that's one of the many diagrams which would then arise from this term here. So diagrammatically, what you would end up doing is to look at all the possible topologically distinct ways you can link these different types of excitations. So at the end, you just end up with a 2-particle, 2-hole state, which is the one you want here. And that has a specific excitation level. So when you look at all the operators you can set up, and these excitation operators here, it's a more matter of fact of matching the different types of particle-hole excitations. And then you can, instead of doing the contractions, you can draw diagrams. But it's always useful to do both, actually. So tomorrow we are going to finalize this discussion by looking at how we can use this to set up the T1 and the T2 amplitudes. That's going to give us much more equations to solve, but it's doable. If you add triples excitations, then you get many, many more excitations. So from a practical point of view, copper cluster with single excitations and double excitations is the standard recipe which people typically use in copper cluster theory. So I hope this looks like a very, more intuitive way of setting it up. But at the end, when you do the set of the equations, you have to go through the contractions. So the gritty nitty paperwork has to be done, or you can encode it and have a program which finds all the contractions for you and sets up the equation. Symbolic Python has actually a package which does this. Yeah. On the, there's a question in chat. Okay. Let's see what it says here. Yeah. So that's one of the things, the final exam, if you are not able to be here physically, that can be done via Zoom. So suppose you have to travel back home, or you are away for some reason or the other one, this is something which can be done via Zoom also. So I'm going to set up a proposal for a schedule, and then you can change among yourself. But I was thinking of using Monday the 15th and the 16th. So I will just make a suggestion, and then if you don't like my suggestion, we can always iterate a little bit. Okay, we can discuss that in more detail tomorrow. Okay.